basic researcher, but I'm becoming more interested in applications of research. So that is part of the content that I'm going to talk about today. The French cognitive neuroscientist Stanislas Dehaene has said that there are 4 basic requirements for learning to happen. So we need attention, we need active engagement, we need error feedback, and we need consolidation. That we need to translate, so to speak, the information into a more permanent code in our minds. But there are a series of challenges to these requirements as well. Attention is easily distracted, it's difficult to sustain over time. Active engagement is, well, requires effort and often is resisted. It's something that we usually don't like. Error feedback, it might be, that is, feedback from the environment might be delayed or might be absent or might be unclear. So what is exactly is to learn from something can be unclear to us. And the consolidation is also very fragile, easily disrupted from a number of different reasons. So what I would like to do today is to demonstrate some of these challenges for you. Maybe you will experience them yourselves. And then I'd like to suggest one approach to meet these challenges. So there are many of them, and I'm sure we all are working on it when we communicate or try to teach someone something. But the approach that I'm talking on today is not that common yet. So first, a crime scenario.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away.
Sorry, madam.
It's just a matter of observation. The real question is, how observant were you?
Action.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
So we have this idea that the world is continuous and that we notice everything that happens. I don't know if this, maybe you did. Did you notice all the 21 changes? I think the typical reaction is that no one notices anything at all. So there's one limitation. Attention is limited. Here are 2 different images with a relatively conspicuous difference between them. Please raise your hand when you see the difference. Oh, simultaneously. So here it is, for those who didn't see it. But now it's easy, right? For everyone. So this blank gray screen in between functions as a rubber, basically, on our iconic memory, so that the information cannot be transferred to more permanent memory systems. And when we don't have that, we have to search serially from area to area until we just, by accident, happen to have our attention on that particular spot. So there are a large number of demonstrations like this from cognitive psychology. But even when the critical information is in plain sight, we often do not see it. So I don't use this, I don't play this video anymore because, well, it's old and most people have seen it. I don't know if you have. What happens here is that we are asked to count the number of times a basketball is passed from one person to another. And what happens in between is that a person in a gorilla costume walks into the scene, pounds his chest and goes out again, and about half the audience will not have noticed the gorilla. Even if, of course, you know that the vision system sees it, right? So we can measure visual activity related to the gorilla in the brain, but it doesn't reach consciousness. Because the consciousness is, or attention is busy with something else. So there's a limited capacity and things can happen right before our eyes and we don't see it. And it doesn't really help even if we are experts. So here, these researchers put the gorilla into the lungs on a CT image and had the radiologists evaluate this. And the radiologists were better than the random participants in identifying nodules in the lungs, but no better at finding the gorilla. I don't know if you see the gorilla yourself. Here it is. You can see that on this side, this is eye tracking. You can see the radiologist actually looked at the gorilla but didn't notice it anyway. So it doesn't help if we're not looking for it. And this is, of course, relevant also for secondary findings when you are referred for some special specialty investigation in hospitals. So here's a different kind. We now talked about limitations in space. There's also limitations in time. So this is the attentional blink phenomenon. So we'll have a relatively slow version. So what is happening, I want you to look at the red square, and then on the same spot there will be a series of letters, and one of those letters might be an X. And I want you to find the X if it's there. Everyone saw it? Okay, so now we're going to do it a little bit faster. Was there an X? There was. Okay, so now we'll do a slightly different version of it. You can see it here, there's a white letter. What I want you to do in the next one is to identify the white letter, and then after that determine if there was an X. You ready? Was there a white letter? And the identity was? Okay. Did you see an X? You did not see an X. How many did? Okay, right. But 20%, 15%? There was an X. But we didn't see it. It was in the same location as in the previous trial, but now we didn't see it. Right? We had to identify the white letter, and then the X vanished, so to speak, for most of us. This is a typical finding. So what we see here is the relative time of the probe target, that is the X, after the white target, and this is the accuracy. So we see if it comes directly, if X comes directly after the Y, we are equally good at identifying it as if we didn't have the first task, that is identifying the white letter. And we also, if it takes a lot of time, that is more than half a second or so, but if it takes between, let's say, 150 and 450 milliseconds, accuracy drops dramatically. So this is the attentional blink. It is as if attention blinked, like an eye blink. We are functionally blind to what is happening in this time window, given that we have a secondary task, or a first task in this case. So this has implications. So to sum up on this, attention is a crucial component of consciousness. We need attention to be conscious, at least in most cases. But it demands effort and depletes cognitive resources. Some people value mental effort more than others, which affects how we deploy attention. And what is also a finding is that what we attend to is often shaped by properties of the stimuli themselves and the task demands, and not that we actually choose to do. We have this feeling that we choose what to pay attention to, but this is true only to a limited degree. So, in terms of learning, well, if we succeed in winning someone's attention when we teach, for instance, or when we communicate somewhere, is this something that is sufficient for someone to learn something or to remember something? Well, no, clearly not. So, as Daniel Schachter writes in his book, 7 Sins of Memory, transience is one of the major sins. In this case, we forget. We forget fast as well, and we've known that in psychology for a long time, and everyone knows that, of course. This is from Ebbinghaus's own studies published in 1885, where he trained himself on some so-called nonsense syllables for days, and then tested himself again and again at various intervals. And as you can see, after 20 minutes, it's only about 60% of the information is left. An hour, about 40, a day, about 33%, and so on. So this, I mean, even if people are attentive, we forget at a high rate. So here's part of the solution I want to propose. What if we can boost memorability? And maybe if we can do that, the memorability of the content itself, not trying to change people, but changing the content to adapt it to people, to people's psychology, if you like. So there are studies that have shown that the extent to which a stimulus will be remembered is largely determined by the features of the stimulus itself, not by the observer's traits. It's not a common way of thinking about memory, because we think of memory in terms of individual differences. Some people learn well, others learn less well. But given that this is the case, memory performance in one group of people is a good predictor of memory performance in another group of people. So having some data from humans, we can say quite a lot about what other humans are going to remember. And more than that, we can train artificial neural networks on memory data. And if we do, then we can generalize the predictions to also untrained content, also content that we do not have memory data from. In that case, if this succeeds, we can sort of lift this retention curve. So they will still be forgetting, but if we idealize or optimize the content, then we can have better retention. That is the idea, at least. So here's a strategy that we've been working on for some time now. We have cognitive neuroscience research, different kinds of phenomena, what people remember and don't. And then we have some idea in now our startup, Mentalese. So Mentalese, I know it's a bit pretentious, but it's we go for it. Mentalese means basically the language of thought or the language of mind. So if we can sort of translate the content to the language of mind, maybe that is a better fit for people. And then we run large-scale behavioral experiments, usually online, and we use that information to train AI models, and then we can sort of put in our content in the AI models and get it improved, like in generative AI, or we can simply get predictions. Will this be remembered or not? So we have worked on this on images, and we find that, as we see here, high memorability information is remembered better instantly and is retained better over time as compared to low and medium memorability images. When we track people's effort, we find that when people retrieve the information about high memorability information relative to low, pupil sizes are smaller, meaning that they invest less effort. This is a well-known finding. If we have to invest effort in something, our pupils are larger. And also we have brain imaging data showing that if we have high memorability images, then there are certain parts of the brain that are much more active. So it's easier access, it wins priority in the brain, so to speak. So we tried the attentional blink and discovered for ourselves, I hope, that we were functionally blind, basically, given that the stimulus was in this attentional blink period, right? We didn't see the exit, we had that as a secondary task. What if we take away the letters and put in images and manipulate the memorability of the images? So like in this case, we have a target, which is at lag 3, that is the third image after the first target, and that can be high or low memorability, and the flankers can also be high or low memorability. So what happens in this task is that there's a colored square, which we have to notice the color of, because we will be asked after. And then there's a series of images presented equally fast as the letter, so it's quite a difficult task. But then we see that when people are supposed to guess which image was the target, can they actually do it? They should not be able to do it, because this is within the attentional blink, right? So let's try. Quite fast. You need to be well prepared. Focus on the cross. Okay, so my fault. I didn't tell you a critical thing, did I? You get a second chance. The target has a red square around it. That's important, isn't it? So the target has a red square around it. So what we have to do then is to notice the color of the square in first, and also notice the image that is surrounded by a red square. Okay, try again. Okay, what was the color of this colored square? Blue, good, everyone saw that. Which of these was the target? The tree. Good, you're correct. That means that you must be very intelligent, all of you. Okay, let's try another version. Again, notice the color of the square and also notice the image that is surrounded by a red frame. This was equally fast, right? Equal number of images. Color? You're correct. Which image? Okay, 1, 2, or 3? Okay, so it was number 1. So these are results from an experiment we did some time ago. So this is from the first stream we saw. And each of these dots are the frequency of responses for an image. So each dot is an image. As we can see, it is the third image that is the target. And if you have a low memorability, high memorability, low memorability, then we can see that people take advantage, or their brains take advantage of the high memorability of the target. So it's much more common to report the actual target as target if that image has high memorability and the competition has low memorability. So this dashed line is sort of the chance level. So all the other responses are under chance level. So even if this is in the blink period, the high memorability of that image sort of demands priority in the brain. It actually works. I think the really interesting thing is this, what happens. Here we can see that it is more common to report picture 2 or picture 4 than the actual target. So these have high memorability and they sort of hijack the brain, so to speak. And we make a mistake, we sort of transfer the red frame to the wrong image and report the wrong image. Again, this is within the attentional blink. It shouldn't happen, but it happens. So this memorability actually it's quite a powerful effect, I would argue. So we have transferred this also now to text. So this is from our website where everyone can log on and try it out for themselves. What happens here is that you can, as a user, put in your text that you have written yourself, or you can cheat and have ChatGPT do it for you. Whatever it is, you can copy it in, and then the model will read the sentences and evaluate to what extent it thinks it can improve the memorability of the sentences. In this case, the last part is in green, so it's quite confident that it can do it. So I click that, and up comes different versions that the model predicts will be remembered better by people. So there are multiple versions because it might fit more or less well with what you're trying to say or the context that you're saying it in. So there is some context built into it. So it evaluates 3 or 4 sentences before and after the sentence in question. But we think that, of course, we have a lot of subjective opinions about the different sentences that it suggests. There are different styles and and all that. But empirically, there is a high likelihood that these sentences will actually be remembered better than the original. And when we have tested this with people, where they suggest their own text and then have the ability to use the model for improvement, about 80% of the cases they choose a suggestion from the model, but not always. Is it actually remembered better? Yes. So this is data from around 4,000 sentences, 2,500 participants, and see here that the low memorability, well, it resembles quite a lot Ebbinghouse's forgetting curve, but it seems to be a lift there for the high memorability sentences. Yeah, so this is more like the distribution of improvements. On average, just over 80% of the sentences are actually improved, and the average improvement is around, well, just shy of 30%. Yeah, so we think of different use cases. Of course, we are going for marketing and advertising, so that's a possibility. We can use it in education, we can imagine. So in this case, we have tried to say something about photosynthesis is more or less memorable. This is actually a more memorable version, so you can use that to improve your slides or your textbooks or articles or whatever. And also for content producers of different kinds. So even if you produce video, there is some script, there is some text to it, and then you can use the text, or you can submit the text to the model and see if there are ways to improving it. So, well, if I ask people, is this actually improved? Of course, I will get many different opinions on that, and it depends on style and everything like that. But empirically, this sentence will be remembered better than that. Yes, so to conclude on this, attention is based on limited capacity, and memory is transit. And boosting content memorability then modulates forgetting by elevating retention early on and decelerating its decline over time. And training AI on large-scale memory data has, we think, a great potential for prediction and generation of high-impact content. And we think it is a promising approach that is complementary to other approaches which try to improve learning through learning strategies, for instance, where we try to, well, train people to behave differently or learn differently. But here we don't try to do that. We simply change the content instead. So, thank you.